Hi guys, welcome to today's lecture. Today we are closing the chapter of descriptive statistics and we are opening a new chapter on introduction to inferential statistics. Particularly, we will see what inferential statistics is, then we move on to cover sampling methods and point estimation as well as interval estimation. Inferential statistics is a set of statistical analysis tools that use sample data to draw conclusions about population patterns. For instance, we use data from 100 students at the UAF to study the average age of the whole students population. In general, in inferential statistics, we draw a representative sample from the population, analyze the data from that sample, and then draw conclusions based on the analysis of sample data about the whole population. Hence, sampling is an important first step in inferential statistics. In fact, selecting a representative sample is at the heart of inferential statistics. Sampling itself is a process of selecting a portion of the population. There are different methods to draw a sample, starting from simple random sampling, systematic random sampling, stratified random sampling, cluster random sampling. In simple random sampling, you have the list of all n population members and you ask the computer to select n of them. Remember, n capital is the number of population members, n small is the number of sample that you want to draw from that population. And you ask the computer to draw this n as your sample. The benefit of simple random sampling is that it draws a representative sample. The drawback is that it requires the list of all population members. For example, in this figure, as you can see, we have the whole population here, and we ask the computer to draw a sample from this population for us. What computer does, the computer gives all members in this population equal chance to be selected, and then draw a sample. In systematic random sampling, you select the first observation or the first member of your sample randomly, then you select each jth observation. Jth observation means each second, each third, each fourth, each 10th observation. Pros of this method is that you do not need the information from all population members. The cons, you may end up non-representative sample. As you can see in this figure, the first sample member is being selected randomly, which happened to be the second person. Then they have selected each third person. So they did not select 3 and 4, they went for number 5. They did not select 6 and 7, then went for number 8. And so in stratified random sampling, we have a population which consists of different stratas, which we call it groups, stratas or groups, which are heterogeneous. That means groups are different from one another. For instance, if we want to select a sample from AUAF students population, we first divide the population into 5 stratas. Then we select a subsample from each of these subpopulation. Then at the end, we put together all the subsamples, all those 5 subsamples, and that is our sample. How we select subsamples from the subpopulations? This is randomly or systematic random sampling. You can see in this graph, we have a population with 3 stratas: first strata or first group, second strata, second group, third strata, third group. Then what we have done is we have selected a subsample from each of these stratas, and then we have put together all those subsamples and to get our final cluster sampling. The population consists of several homogeneous groups. Each of these groups called a cluster. Then what we can do is we can randomly select one or more of these clusters and take all members of those selected clusters as our sample. For instance, you want to take a sample of farmers from a district consisting of many homogeneous villages. Then what you can do is you can select one or more of these villages randomly and then interview all farmers in those selected villages. The benefit or the positive side of this method is that it's easy and cost efficient. The cons is that it's hard to find instances where the conditions are satisfied, meaning that it's very hard to find a population which consists of a lot of clusters, which are here. We have 1, 2, 3, 4, 5, 6 clusters. And then what we did was we selected 2 of those clusters. Once we have selected our sample, we go ahead and follow the steps in our statistics. That is, we collect data from the selected sample, then we clean the collected data, and we analyze. First, we apply all descriptive analysis techniques, both univariate and bivariate, and then apply inferential analysis techniques. Why? Because we are having now sample data. In inferential analysis techniques, we have two sets of analysis techniques: univariate inferential techniques, bivariate inferential analysis. Today, we start with univariate inferential analysis techniques. Today, we cover the first univariate inferential analysis technique, namely point estimation. The point estimate of an unknown population parameter is its corresponding sample statistic. The point estimate of population mean mu is the sample mean x bar. Likewise, the point estimate of the population standard deviation sigma is the sample standard deviation s. The same way, the point estimate of the population proportion p is the sample proportion p. The more representative the sample is, the closer is the point estimates to the corresponding population parameter. The second univariate inferential analysis technique is called interval estimation. An interval estimate of an unknown population parameter is actually a numerical interval that contains the parameter with certain degree of confidence. 3 degrees of confidence are more common in practice. There's 90% confidence interval, 95% confidence interval, and 99% confidence interval. Among other parameters, here we consider the interval estimation of the mu, which is the population mean. For population mean, 90% confidence interval is x bar minus 1.645 s over square root of n, the lower bound, x bar plus 1.645 s over square root of n, the upper bound. The same is for 95% confidence interval and 99% confidence interval. X bar is the sample mean and n is the sample size. To calculate the confidence interval in R, we need a package called RMISC. Please install this package before coming to the class. Then we library, I installed it already, I library it. Then calculate the confidence interval for the average age of the population using the data from a sample which I have selected from the population. Then use CI confidence interval $$age. Then I want to calculate, for example, the 90% confidence interval. Run 90%. What you see here is 3 things: upper bound, the mean itself, mean is 25.8 years, and the lower bound. What we can say is that with 90% confidence, we can say that the mean of the age in the population is between 23.69 years and 27.9